So welcome everyone. I'm Judy Black. I'm the president of Halifax Center for 2021. It's my second term as such. And I'd like to welcome everybody from the center as well as those from near and far. So welcome. We hope that the topics we're addressing today will provide a lot of interest and spark some energy amongst us all. We have our keynote speaker today, Kaja Rotermund, is here, and we'll introduce her more formally in just a few moments. But we have some of our members as well telling us what's going to be up in the night sky, provide some entertainment, so to speak, with our food for the soul, as well as other things. For those of you who are attending today's meeting and are not currently members, I'd like to certainly encourage you to do so. There are several perks to becoming a member. One of them is all the stuff you get. For instance, the Observer's Hand Guide, or Observer's Handbook rather. This is the newest edition, and just as a matter of note, there are several of our center's members who are contributors to that particular product. We also get the Journal of the Royal Astronomical Society, and I'll point out something special about the latest edition later in the talk. You certainly get a subscription to Sky News, which is a really interesting read for both new and experienced observers. And new in the past year, you also get a copy of Explore the Universe, which is one of our certificate programs that anybody, member or not, can participate in. And you can also purchase the workbook that goes with the guide, that particular guide. And it provides you as well with the observing forms and whatnot for the program. As a member of RASC, you also get access to the robotic arm, as well as the RASC national discussion list. Locally, you certainly have access to our own discussion list. You get access to our Nova Notes, which is our center's newsletter, as well as our other center resources, which are our library and the St. Croix Observatory. And most importantly, you have access to the membership. It's an incredible group of people with a lot of energy, a lot of expertise that they're very much willing to share. So that's the greatest thing that's about this organization. And Happy New Year, everyone. We are the start of 2021. Hopefully it will be a gentler year than 2020 has been, and hopefully observing can continue in the way it has been done over the last 9 months, but hopefully we can get back together and actually gather face to face and enjoy those night skies together in a more informal way. And also happy birthday to everyone who's had a birthday since the last time we met, and those who will be celebrating till we meet again in the beginning of February. I'm going to share my screen and tell you about the agenda that we have for today. So welcome. This is basically our agenda. Following this, Paul Gray will do his photo montage, which is a collection of the sketches and photos that have been put forward by members over the past month. Our special guest, as we've noted, is Kaja Rotermund, and she'll be discussing gravitational lensing by a galaxy. Paul Heath will do his regular presentation on Food for the Soul on the Christmas Stars, the name of his poem this month. Dave Chapman will do What's Up in the January Skies. And if you'll note, Dave, I actually had the right month this time. And then we'll close with the news from the board. Once we have adjourned, we have an informal Astro-Chat. The recording is turned off, and I will tell you now that this is being recorded for use and posting on our Halifax RASC YouTube site. But the Astro-Chat is not recorded. Recordings are all turned off during that. It's very informal. One of the things that we'd probably like to discuss on that today, if members are willing, is to talk about Nova East and what do we do about it this year. So just kick around some ideas on that. So that is our agenda. So having said that, I'm going to pass the screen now over to Paul Gray, and he can do the montage. Paul?
All right, Judy. Hello, everyone. I'm assuming you can hear me, so that's good. I'm going to try and share my PowerPoint, see how this goes. Should be seeing it now.
Yes.
Good. All right. It's going to be a short one today, mainly because here. It's been cloudy, a lot of cloudy. I think other than a bunch of shots of the conjunction and the sun, there's not a whole lot in here. So I think we got 16 slides this month, whereas I think 2 months ago we had 70. Just goes to show how bad it's been.
A lot of people got astronomy stuff for Christmas, obviously.
Yeah, somebody's been buying too much stuff because we've been having horrible cloudy weather. But there's a lot of people had a chance to see the conjunction, which is nice. Too bad we missed the prime day, but a lot of pretty photos to jog those memories that for those of us who just popped out to look. I'm not going to chat about any of them. I'm just going to let it roll through here. But yeah, it's been a horrible month for observing, if you ask me. And there aren't many other photos posted to the Facebook groups that I don't grab either. I'm just grabbing what's been sent to the email list, just for those people who are wondering if they don't see theirs or why there's not more. They've seen some on Facebook that we don't show here. And I will grab sketches. Dave, thank you for your sketches. Good news, the sun's getting active. So that's nice to see.
Hey, could people make sure that their sound is off, please?
I think that's it. That is it.
Great.
So I'll stop
Thanks, Paul.
sharing. Again, send your emails to the email list with your photos. Send them directly to me if you want, and I might start grabbing them from Facebook as time permits in the future.
Okay, thank you. That's great.
You're welcome.
Okay, our next item up on the agenda is our special presentation. I'd like to thank Dave Chapman for bumping into this person at another event. Without that chance meeting, we would not have had Kaja attending today. So Kaja's a recent grad in the physics department at Dalhousie University here in Halifax. And I'm going to read this because I cannot memorize it. Over the course of her PhD, she focused heavily on gravitational lensing, identifying massive elliptical galaxies acting as lenses in front of high redshift sub-millimeter galaxies, making use of multi-wavelength photometry, primarily across the optic and near IR regimes. And this will be the topic of her presentation today. Kaja has also spent some time developing the cold readout electronics currently implemented by cosmic microwave background experiments such as Polar Bear 2 and SPT-3G during her time as a visiting student at UC Berkeley. So it's with great pleasure that I welcome Kaja and welcome her to Halifax Center and being our presenter for today. Thank you.
Yeah, thank you for inviting me. I will share my screen as well. And then hopefully
get started.
So you guys see the title slide?
Yes.
Okay, great. So yeah, good afternoon. Happy New Year to everybody. And thank you again for inviting me to speak today. Yeah, so my talk is going to focus a lot on the South Pole Telescope and the very exciting objects that it has detected since its first light in 2007. And a lot of those objects were detected through the use of gravitational lensing. I'd like to point out that a lot of the work that I'm going to be presenting today was conducted by the entire SPT SMG working group, and just mentioning specifically my PhD supervisor, Dr. Scott Chapman, and then some other collaborators, Kedar Padek, Riley Hill, and Dr. Joaquin Vieira, who've been instrumental in a lot of the work. I would like to just ask, if you have any questions, feel free to ask throughout the presentation, and I'll be more than happy to answer as they come, or answer questions at the end, whichever seems to be easiest. Okay, so I'm going to try and tell a little bit of a story today, and I'm going to start with the South Pole Telescope itself, and then I will move on to the sub-millimeter galaxies, which were somewhat unexpected detection by the South Pole Telescope, as well as the effects that gravitational lensing has on them, and then the very rare cases where gravitational lensing is not playing into the detection of sub-millimeter galaxies, and these are protoclusters. So hopefully, if some of these words didn't mean anything to you right now, by the end of my talk, these words will mean something to you and you'll understand what I'm talking about. So to begin with, the South Pole Telescope is located, as the name would suggest, at the geographic South Pole on the Antarctic Plateau, specifically at the Amundsen South Pole Station. And this is one of the best sites in the world for observations of the night sky because it has very low water vapor content in the atmosphere and is also extremely stable water vapor content. This location also benefits immensely from the circumpolar nature of the apparent motion of the sky, meaning that the sky appears to be motionless because the South Pole Telescope is beneath the celestial South Pole, and so observations don't need to contend with objects rising and setting in the same way that telescopes, for example, here would have to contend with. SPT is a 10 meter telescope, and it observes 2,500 square degrees of the sky. This is about 6% of the full sky, so it is quite a significant and large scale survey. It observes at 3 different selection wavelengths, 1.4, 2, and 3 millimeters. These correspond in frequency to 220, 150, and 95 gigahertz. I'm just putting that out there because I'm going to kind of be switching back and forth between gigahertz and millimeters, which might be a little confusing. The telescope also is sensitive to polarization, which is important for some of its observations. So one of the primary science objectives of the South Pole Telescope is to measure the temperature and isotropies as well as the polarization of the cosmic microwave background. The cosmic microwave background is this ubiquitous 2.7 Kelvin radiation that is observed in the microwave wavelengths and is the first light that we can see after the Big Bang. Now, the temperature of the cosmic microwave background is actually very consistent across the entire sky at this 2.7 Kelvin, and any fluctuations or anisotropies in the temperature are only on the scale of 200 microkelvin. So any of these fluctuations you see here, the dark blue being colder, the red being warmer, these are just minute tiny fluctuations. And so you need telescopes with really high sensitivities in order to detect these fluctuations. Another primary science objective of SPT is to detect massive galaxy clusters via the Sunyaev-Soldovich effect. And this is what I'm going to be this objective of SPT is what I'll be focusing on in the coming presentation as well. Here's just an example image taken by HST of the galaxy cluster Abell 1689. You can see this huge conglomeration of massive galaxies, all gravitationally bound to be one massive structure. Okay, so the Sunyaev-Soldovich effect is actually makes use of a fairly simple first-year physics phenomenon known as Compton scattering, in which you have inelastic scattering of a photon off of an electron. And because it is inelastic, the kinetic energy is not conserved in the scattering. So in Compton scattering, you have a high energy photon that as it scatters off of the electron, loses some of its energy to the electron, and the electron ricochets with some increased energy. The reverse is also possible, known as inverse Compton scattering. And this is where you have a low energy photon that gains energy from a moving electron as they collide. And so this is depicted in this cartoon where you have a low energy photon, low frequency in red, colliding with a high energy electron. That electron passes some of its energy to the photon, and you've got this high energy, high frequency photon that results. This is known as upscattering and is how the Sonya-Soldovich effect works. And so here we've got a little cartoon. The way that the Sonya-Soldovich effect works is you've got these low energy photons from the CMB, from the cosmic microwave background at 2.7 Kelvin, that are streaming through the universe. When they come into contact with a massive galaxy cluster, the high energy electrons in that galaxy, in the intracluster medium of the cluster, will impart some of their energy onto this low energy CMB photon, and then we are left with this blue shifted or increased energy CMB photon that we then observe here on Earth. So this is inverse Compton scattering of a CMB photon through the intracluster medium of a cluster that we then observe. And this shifting in energy results in a spectral distortion of the cosmic microwave background maps that I showed you earlier. These effects are really small, but our telescopes are able to observe that. So to show you the effects of this shifting of the energy in a plot to kind of show the actual results. So here we have a plot of the change in intensity of the light as a function of frequency, and the dotted line shows what a quote unquote regular photon, CMB photon, would look like, the intensity there. If this photon comes into contact and interacts with a galaxy cluster, then the peak of the intensity of these photons shifts to higher frequency, as I mentioned earlier. And there's also a corresponding decrement in the intensity at lower frequencies. So that's the solid line that you see here. It first dips below and then comes back up high. And as you can see, there is this crossover or null in this intensity plot. And this is really critical to the Sonya-Soldovich measurements that SPT conducts. So here is an example of the full sky, or not full sky, the full SPT coverage at 95 gigahertz. And you can see it looks fairly similar to the temperature anisotropy image of the CMB. This is at 95 gigahertz. And so one of the key differences between the effects of the Sonya-Soldovich scattering and the temperature anisotropies is that they act on vastly different angular scales. So these temperature anisotropies are over very large scales. The CMB or the Sonya-Soldovich effect is on much smaller scales. But on a more practical matter, how do we actually observe or determine if we've observed a galaxy cluster? And that is where the three different observing wavelengths of SPT come into play. So we observe at 95, 150, and 220 gigahertz. As I said, those were the 1.4, 2, and 3 millimeters. And at 95 and 150, if you look back to the intensity plot on the left, those are in the regime where we see this decrement in the intensity. And so we see this dark blue dot, which shows that there are less CMB photons reaching us at these locations. However, at 220 gigahertz, which is right where the crossover exists, this decrement disappears. And so this is the exact key feature that we're looking for in order to find clusters of galaxies. So here is in gray an image of the SPT map that we're observing. And if this is, for example, a 95 gigahertz map, then what we're looking for are these shadows or these dark spots, these just kind of point-like dark spots, which would suggest that there's a galaxy cluster there. We then compare to the same map at 150 and 220 gigahertz. And if we see the same effects that I just showed in the previous slide, then we can confirm that a galaxy cluster actually exists there. However, if you are looking very carefully at this map, you might also see that there are some very bright point-like sources. So not shadows, but bright sources. And it turns out that these are actually either active galactic nuclei or the most distant star-forming galaxies that we have detected. And this is kind of going to shift directions from the galaxy clusters and move on and talk a little bit more about these very bright star-forming galaxies that were a fairly unexpected detection by SPT. As I said, this is the secondary, unexpected yet exciting science that SPT can conduct, and it's the detection of these rare, bright, high redshift, dusty star-forming galaxies. So that's quite a mouthful, and I'll go through each of those points one by one. But first, I want to draw your attention to this cartoon in the bottom right. So if you have an active star-forming galaxy, you've got a lot of young and bright O and B type stars that emit radiation predominantly in the UV. If you have a lot of gas and dust present surrounding these young stars, then the dust will absorb that UV radiation and re-radiate it in the infrared. And this thermally reprocessed light, if you have a galaxy at higher redshifts, this infrared light will then be redshifted to longer wavelengths, potentially into the submillimeter and millimeter, and therefore detectable by SPT. And so the fact that we have these point sources that are being observed in the SPT maps means that we have galaxies that are host to massive gas and dust reservoirs, which therefore implies we have these huge thermal dust radiation, which is observed in the submillimeter. These galaxies have to be forming stars very actively and very rapidly in order to have enough thermal dust radiation that we can observe, or enough UV light that can be reprocessed into thermal dust radiation. As I said, they also have to be at high redshift because this reprocessed thermal light is actually in the infrared, and that needs to be redshifted into the submillimeter for SPT to detect it, and so they have to be at high redshift for that to occur. And because these galaxies are brightest in the submillimeter, they have been coined submillimeter galaxies. SPT has a fairly high detection threshold at about 20 milligensky at 1.4 millimeters. And so that means that SPT is only detecting or selecting the brightest of these point sources, which consequently also means that they're fairly rare objects that we're observing here. Only about 200 of these point sources were observed in the initial 87 square degrees that SPT mapped, and less than 25% of them were determined to actually be submillimeter galaxies. The remainder were other objects such as active galactic nuclei and lower redshift objects. So these are very rare objects that we're observing here that were a very unexpected find by SPT. So yes?
There was a question about what would be the rate of star formation?
I will get into that. That will be a next slide, yes. To get a little bit more nitty-gritty into the detection of these galaxies, here we have a plot of the spectral energy distribution of, for example, galaxies. And so the spectral energy distribution is just essentially a plot of the brightness as a function of wavelength, or the flux density as a function of wavelength. And you can see that each of the 4 different types of galaxies have features that are similar between them, but have different intensities. And so the young and hot, bright stars that emit in the UV create this initial small hump in the spectral energy distribution. The colder, less massive, older stars create this second hump that is significantly larger. And then we have a third hump, which is this reprocessed thermal dust emission. And you can see for ellipticals in green and the disk galaxies in purple, the emission from the old stars is the primary emission of the galaxy. However, if you look at the red curve, the starburst or submillimeter galaxies, go back one more, the thermal dust radiation dominates over the radiation from the cold stars. And so if you're trying to observe any of these galaxies, you would strategically choose the right wavelengths at which it is brightest to detect them. Now, these starbursts or the submillimeter galaxies in red have an additional benefit that the submillimeter observations can make use of. And that I'm going to try to explain in this plot here, which is a little bit overwhelming upon first glance, but it shows the negative K correction. So this is, again, the flux density or the brightness as a function of redshift now. And so I'm going to kind of go one line at a time. The black line shows the flux density for optical observations. So if you imagine a galaxy locally that you're observing at optical wavelengths, as you push that galaxy to higher redshifts, you'd expect the brightness or the flux density to decrease because of cosmological dimming. Moving further away, you see the flux decreases. If, however, you are able to conduct the observations in the submillimeter, so that would be these red and the reddish and brownish curves that have like a saddle point there, you see that the flux density appears to be roughly constant as the redshift increases from redshift 1 to 10. And so this is really critical for the observations conducted by SPT, because it means that essentially the negative K correction means that the rising dust temperature or rising dust spectrum of these galaxies compensates for any of the cosmological dimming. So as the galaxy moves to higher redshift, because we're observing at increase along the thermal dust radiation on the spectral energy distribution, it's rising on the hump there. We're actually sampling brighter parts of the galaxy, and so it appears to remain at the same flux density. And so submillimeter observations result in a flux density that is relatively independent of redshift and is very critical to observations of SPT. So that was a little bit more detail on the observations, but now to get into submillimeter galaxies as a whole, this will talk about the star formation rates here. So here I've got some parameters of submillimeter galaxies in comparison to our Milky Way. And so submillimeter galaxies, as I mentioned, are brightest in the submillimeter, and their far infrared luminosities are up 2 to 3 orders of magnitude larger than the luminosity of our Milky Way. So they're really bright. They're also at much higher redshifts and are very young. So their median redshift of the submillimeter galaxy population is about 2.5, with a higher redshift tail. So a lot of them, the ones that we found, actually exist up to redshifts 4, 5, and 6. So they're very high redshift. They have large gas reservoirs. As I said, they need to have a lot of gas and dust to reprocess that stellar light. So they have large gas reservoirs, again, about an order of magnitude larger than our Milky Ways. And the star formation rates are really high. So they can be anywhere up to 1,000 solar masses per year or even larger in some cases. And this is in stark contrast to our Milky Way, which is just forming 1 to 2 solar masses per year. So these are very active galaxies at very high redshift or very early in cosmic time. And then because of the high gas content and the high star formation rates, they also have very large stellar masses. Again, order to magnitude larger than our Milky Way. Okay, so because SPT has this very high detection threshold of about 20 millijansky, we are only selecting the absolute brightest sources. And this means, consequently, that a large percentage of them actually are gravitationally lensed. Gravitational lensing is a consequence of Einstein's theory of general relativity, in which the light from a distant object is magnified and bent as it passes around the gravitational potential of a massive object in the foreground. And so in this cartoon here, the foreground lens galaxy is this bright white object. The source, or the submillimeter galaxy, in the background at high redshift is a small little red dot sort of to the left. And you can see that the light is being bent, and then what we actually observe is this image of the submillimeter galaxy on the far left. And this image has the characteristic morphology of gravitational lensing, where you have these arcs and circles around the central lens, and these arcs are known as Einstein rings. And so this lens in the foreground is sometimes referred to as a cosmic magnifying glass, because it allows us to see these high redshift galaxies, which would otherwise be too distant or too faint for us to detect, because it is magnifying the brightness of the galaxy in this bending and distortion process. And so we can observe galaxies that would have otherwise not been visible to us. So kind of a quick historical perspective or interlude. While Einstein did predict this effect of gravitational lensing, it was Zwicky in 1937 who first hypothesized an actual visible effect on a galactic scale. And he used the most massive nebula known at the time to predict that the separation of these images would be on the order of 30 arc seconds. And he thought that the images would be magnified, or the brightness would be magnified up to 100 times. It took another 40 years or so before Walsh and his team detected the first multiple imaging of an object. They observed a quasi-stellar object, which was, or two images of a quasi-stellar object, which was separated by about 6 arc seconds. And the spectra of these objects clearly identified the two images to be the same object, or to be physically associated with one another. Walsh and his team were fairly skeptical of the actual chance alignment necessary for gravitational lensing, but they did conclude that there was a very high likelihood that these two images were indeed the same galaxy. And so since then, there's been a very large concerted effort made to find these gravitational lensing systems that allow us, as I said, to observe galaxies that otherwise would have been too faint for us to detect. And so surveys range from the radio to the optical, and the one that I'm going to be talking about is the submillimeter surveys conducted by SPT. And so here is a paneled figure of some of the submillimeter galaxies that were detected through gravitational lensing by SPT. You can see that some of them have these very strong ring-like features, Einstein rings. Those are the blue-green contours or ALMA imaging of the submillimeter galaxy, the source. And yeah, you see these Einstein rings. Sometimes you see not exactly rings, but just counter images, which we can confirm are indeed the same galaxy. And then the grayscale is a near infrared image of the lens in the foreground. And you see that the vast majority of these indeed have a lens that is very clearly visible, that is centered by the ALMA imaging of the submillimeter galaxy in the background. Yeah, so just to kind of clarify a little bit more, if you have a perfect alignment of the submillimeter galaxy and the lens along your line of sight, then you will end up with a perfect circular image of the submillimeter galaxy around the lens. However, if your serendipitous alignment here of these galaxies isn't ideal, if you've got slight offsets along the line of sight, then you will possibly have an arc with a counter image or just two counter images. Sometimes you may even just have a single image. However, through lensing models, we know that these lenses, even if it's just a single image and there's no clear arcs, lensing models will tell us that the brightness has been magnified, and so they are part of a gravitational lensing system. Additionally, if you have, I'm going to go, I guess, back one more time. If you have if the lens is not a single massive galaxy, but is a group of galaxies or a cluster of galaxies, then you might also result in some more unique shapes that don't result in just nice circles, some of which you can see in this panel here as well. So kind of interesting figures to look at and to study. So the SPT catalog of lenses or submillimeter galaxies, we have confirmed that over 90% of the submillimeter galaxies that SPT detected are in fact gravitationally lensed. And this is through the high resolution ALMA imaging that we conducted and the clear morphologies of gravitational lensing, as well as the clear presence of a lens in the foreground in the optical and near infrared. And the work that I really focused on during my PhD was the study of the lenses of these systems. And I found that the lenses are predominantly elliptical galaxies, the red and dead ellipticals. So they are the brightest in the infrared. we found that there is no preferred redshift for these lenses. They range over very large redshift range. Obviously, they have to be at lower redshift than the submillimeter galaxies. So the median redshift is around 0.9, but you can see by the scatter, it's a very large scatter. So they really do range over a large redshift range. Yep.
There was a comment made where the SPT 0245-63, which is the second row, third from the right, is centered. And they consider it strange. Is there a reason why it would be centered compared to some of the others that aren't?
So this might have something to do with, I was just going to say, the stellar mass of the elliptical galaxies. The stellar mass of ellipticals is not necessarily concentrated at the core. It might be an extended halo. Also, you might have, the alignment might not be perfect here, and that's probably the primary reason. If the submillimeter galaxy was exactly along the line of sight with the lens, then the source would be a circle around it. But if it's kind of offset, then it might appear to be right on top of the lens, just how the geometry works and how the light is being bent around the lens in the foreground.
Thank you.
I hope that answers the question. Yeah. Okay, so as I said, about 90% are gravitationally lensed, so that's a vast majority. But what about the remaining roughly 10%? What's happening here? And so in the high resolution follow-up imaging of these, we found no evidence of gravitational lensing, and there was no evidence of a lens in the foreground in the optical or near infrared. But for a lot of these, it turns out that in the high resolution imaging, the submillimeter galaxy actually turns out to be an association of multiple galaxies. And while these galaxies are typically at the same redshift, they are not the same galaxy. So we've got multiple separate galaxies all at the same redshift. And these we have determined are protocluster candidates. So what are protoclusters? Backing up a tiny bit to kind of talk a bit about the formation of protoclusters and clusters, the dark matter in our universe began as a fairly or near homogeneous distribution with slight overdensities, as is seen in this top panel here. I've chosen a redshift of 4. As the universe expands, though, these overdensities begin to coalesce, growing both in size and in contrast with respect to the surrounding space, and they eventually converge into nodes of dark matter halos, or nodes of overdensities, which are dark matter halos that are connected via this filamentary structure. And the filamentary structure is surrounded by these large voids. And it is along these nodes and along the filamentary structure that gas and dust gravitates and collapses to form galaxies, and in the most overdense regions will possibly form multiple galaxies, therefore beginning to be the seeds of massive clusters. And so at early times where we've just got the initial formation of these multiple galaxies, if we don't have a fully formed cluster yet, then we consider these to be protoclusters. So protoclusters are the progenitors to massive galaxy clusters. And it's a little bit difficult to truly identify a protocluster because the definition of a protocluster is something that will evolve into a fully virialized cluster. However, there's no real way for us to know that they will evolve. We can't observe them over time. So it is a little bit, difficult to truly say. However, we think that, in these protoclusters, you have very large overdensities of very luminous galaxies as well. So you're forming very bright, you've got galaxies that are forming stars very rapidly at these very high redshifts. And so we think we have found a couple of these protocluster candidates in the SPT survey, these unlensed candidates. And one of them is SPT 2349. This is a simulation that was conducted by Douglas Renahan, a collaborator of mine in the SPT SMG group. And this shows the SPT 2349 protocluster, which was found to contain 14 individual galaxies which are all merging and colliding to form a massive cluster core about a giga-year after we are currently observing it to be at redshift 4.3. So that's just kind of a really cool simulation of this really incredible protocluster that we detected. I'm going to kind of go a little bit more into detail about this protocluster. It is the brightest example of a protocluster in the SPT sample. And I'm going to show you the importance of high resolution follow-up imaging. This source, SPT 2349, was originally detected by SPT at 1.4 millimeters, which has a resolution of about 1 arc minute. And it was detected as a point source that was slightly resolved. We then took a look at it because it didn't have any evidence of gravitational lensing. We followed up with Loboka imaging at 870 microns, which has a resolution of 19 arc seconds, so quite a bit of an improvement there. And we found that the source actually resolved into 2 elongated lobes. And in this image on the right, which is a GMOS red, green, blue image of the protocluster, the purple contours show the southern Loboka lobe. There is a northern lobe that this is just the very core part of that southern lobe, and then it extends quite a bit and up to the north as well. And then we also did follow-up imaging with ALMA at 1.4 or 1.1 millimeters, which has a resolution of less than 1 arc second. And here we found 14 individual galaxies, sub-millimeter galaxies. Those are the green contours here. And through spectral analysis, we were able to confirm that all of them had a redshift of 4.3. So this is a very high redshift association of 14 sub-millimeter galaxies, all in this very tight 19 arc second lobe observed by Loboka. And so with further ALMA imaging, kind of ranging further out from this core region, we found another 25 sub-millimeter galaxies that are part of the more extended Loboka lobes. And so we believe that this core of the southern lobe here is the very core area of the protocluster. And as the simulations showed, that these 14 sub-millimeter galaxies will likely merge and merge into one massive, probably brightest cluster galaxy at the core of a massive cluster. And so at the stage that it is right now, we think we have detected the most massive overdense structure that is known in the distant universe at this point. There are other protocluster candidates that have, or protoclusters that have been observed with significantly more galaxies that are part of the system. However, they span a significantly larger area. And so we have 14 in a very compact region, which makes this such an incredibly massive object. And to give you an example of, or put in the size into context, on the left here is this rendering from the simulation of the 14 sub-millimeter galaxies within this 19 arc second diameter, which at redshift 4.3 is about 130 kiloparsecs in diameter. And that's in contrast to, on the right, our own Milky Way, where the dark matter halo size is not fully known, but it is estimated, the radius is estimated to be 100 to 200 kiloparsecs. So these 14 sub-millimeter galaxies of SPT 2349 are no larger or fit within our own Milky Way. But the masses of each of these galaxies, as I showed earlier, are significantly larger than what our Milky Way has, currently has. So this means that this protocluster core is destined to merge into this exceptionally large cluster core as it evolves.
Question for you, Kaja.
Yep.
Are you able to trace the protocluster to present galaxy clusters?
Well, I'm just struggling with the word trace. So obviously we can't observe them as they evolve with time. However, through the simulations, knowing that they will coalesce, and we know that at the core of massive clusters, there is this brightest galaxy cluster, which is generally this massive elliptical galaxy. Through these simulations, we know, and just kind of, yeah, how these galaxies will evolve. They start as these active star-forming galaxies, but because of the intense nature of merger, the stripping and coalescing, they will eventually, when they merge, they will form into a red and dead elliptical galaxy, which is like the brightest galaxy cluster, which is observed in local clusters. So the evolution of how the merger of these clusters, of these submillimeter galaxies in the cluster core is expected to happen, matches with what we see locally in massive clusters. Yeah, so this is just a snapshot of the simulation over various time frames. In the top left, we start at redshift 4.3, the current age, or the current situation of the protocluster with 14 submillimeter galaxies. Then as time progresses along the top row, these galaxies begin to merge with these huge starbursts occurring and extreme energetics happening with various outflows and shocks that are shown by these, it's just very violent reactions. By redshift about 3.3, which is only 500 mega years after the current time, we are beginning to see this single galaxy at the core, and then the activity continues to settle until about a giga-year after current time, which would then be, we think at around redshift 2.7, we are left with this single massive galaxy, which because of the violent nature of mergers, as I just mentioned, will likely just be a red and dead elliptical where all the gas reservoirs have been fully depleted or stripped from the system. And this is likely going to be the brightest cluster galaxy of a massive cluster, probably a cluster on the size of the Coma cluster. Yeah, and so with that, I'd like to say thank you, and I appreciate once again being invited to give this talk, and I'm happy to answer any more questions.
Okay, I open the floor to anyone that has a question. Please remember you have to unmute your speaker. Paul, I see your hands going up. I'm assuming you have a question.
It's a thing they do, and nowadays it's online clapping, air clapping.
Aha, okay.
That's something new we all learned in the last 9 months.
I've learned it from cadets. All the cadets do it. It's a thing. They just do that, and it's considered to be clapping. It's a muted clap.
There you go. Any questions for Kaja?
Yeah, I was asking about we're tracing that the protocluster. I'm wondering if you can actually figure out which of the giant elliptical galaxy cluster, like the core of the elliptical galaxy cluster, came from that protocluster that you discovered.
Well, I don't think so. I mean, it hasn't yet evolved into a cluster. It is still in this protocluster stage. So with enough time, it will likely evolve into something similar to the Coma cluster or even larger. But yeah, we can't like say this cluster here is what this one used to be.
Okay, yeah, that's what I was wondering, if you could actually follow the progression through.
No.
Okay, well, thank you so much for coming. I'm glad you bumped into Dave on that eventful day, and thank you so much for coming today. It's truly appreciated.
Thank you so much.
Interesting.
Happy New Year, everybody.
There were a lot of people that were really excited to have this topic addressed, and really happy that you did that for us. So thank you.
Glad I could be of help.
I've got a question, if I could.
Yeah.
Why is the field restricted to 87 degrees?
That was just the initial imaging that SPT conducted when it, like right at first light, we do now have the full 2,500 square degrees. And so our sample, so I think I said there were 47 submillimeter galaxies initially in the 87. We now have not quite, I mean, the sample that I've been working off of was about 57 gravitational lensing systems. So they are still very rare. And just another point to that so of these, 56 gravitational lensing systems that we found, or point sources, only 10% are unlensed and therefore potentially a protocluster candidate. SPT 2349, and as I said, was the absolute brightest. That's the one, you always choose your brightest and best to start with. So this is the brightest one, and it's just one protocluster of this size that is observed in these 2,500 square degrees. So we don't expect to see anything similar to its size in this same 2,500 square degrees. You'd probably see maybe one for every additional 2,500 square degrees you see. So they're very rare, especially these really large, bright ones. I mean, we do see a lot of additional, or not a lot, but there are more less bright protocluster objects out there, even in our own sample that we are going to be doing follow-up observations on next, but they're all very rare.
Are you going to move beyond 2,500 degrees to another set?
So with SPT3G, we are going to we'll have a lower detection threshold. So we won't only be able to observe stuff that's brighter than 20 millijansky, we'll be able to bring that down to like 10 millijansky. So we'll be able to observe fainter protoclusters. I don't actually off the top of my head know whether or not the expected field of view of SPT3G is supposed to expand. I think it's just looking at the same 2,500 square degrees. So, I mean, you are limited to the Southern Hemisphere. And I think they just continued to look at the same area. They're just improving the sensitivities dramatically for various science objectives, including these protoclusters.
Great.
I have a question for Kaja. First of all, Judy gave me credit for bumping into you. I don't think I can take credit for bumping into somebody, but I will take credit for immediately thinking, when I found out that you were an astrophysicist in our community, I will take credit for thinking that it would be great to have you address our club, and I'm very happy I thought of it. But I have a question, and it may not be fair. You don't have to answer if you don't want to, but I'm curious about what are you doing now and what's next?
Good question. Since I graduated, I've been working still with my supervisor to convert some of my research into papers. And I actually one of the papers just got accepted by Monthly Notices Review. So that's a paper on this 2349 protocluster. And then I'll be focusing on putting a lot of the work on the lenses for these gravitational lensing systems into a paper as well over the next couple of months. And I have just been applying to a whole bunch of postdoc positions. So hopefully starting in September, there'll be a postdoc on the horizon.
Wonderful. There's a couple of questions that have come through on the chat.
Okay.
One is there any plans to do something similar for the Northern Hemisphere? And the other one is, the person has heard that lensing of supernovas can cause light from rings to arrive at differing years. Anything about that?
Yeah, so I don't know about plans for the Northern Hemisphere. SPT is obviously not the only telescope that's observing at millimeter wavelengths, and other telescopes that are probably pretty adept at trying to find these gravitational lensing systems as well. As I mentioned, you can detect gravitational lensing systems at different wavelengths. It just happens that at the submillimeter, we have this effect from the negative K correction that we have a redshift independent sample. So if you're looking at different wavelengths, you have to take biases from those wavelengths into account. So I'm not sure about the Northern Hemisphere, but the gravitational lensing of supernova is actually quite interesting. And I think that has been in the news, well, I don't know, within the last 2 years or so, maybe, for objects that are closer. So not these, like extragalactic objects that are really high redshift. But if they're closer, you can, because the light, if your alignment is perfect along the line of sight, as I said, you'll have this ring of light that you see. If you are slightly off alignment, then you have these like massive arcs with counter images. And because you are slightly misaligned, the light actually has a different travel path and therefore a different travel time from it being emitted from the source and us observing it. So you are able, if you can actually differentiate, if you've got a very fast event like a supernova, where you're not just observing continuously, you're just seeing like an instantaneous burst, so to speak, you are able to see that light arrive at different times, and you see it arrive at slightly different locations because you've got like the arc arriving at one point and then the counter image a week later or something like that. So that is really, really cool effect of gravitational lensing.
Okay, well, thank you so much again. And
Thank you.
you're welcome to stay with us for the remainder of our meeting. I think next up, just let me, if I'm not mistaken, is Paul Heath. And Paul, I do have your poem up if you'd like to. There we go, The Christmas Star. It's not all there, but it will be, not to worry.
Hey, this was the day after the close conjunction that most of us in Nova Scotia missed because of the weather. And the following night was just amazingly clear outside of Halifax. So it's sort of an impression of what I saw at that point. Christmas Star. Once again, the world, plague-feared, looks hopeful to the skies. Foretold a wondrous, gentle kiss will arise, that distance has separated in both time and space, yet lies hidden now by Earth's sympathetic tears. But hope, a tiny kernel swells, the Earth in joy responds. In nervous anticipation, we sweep the skies above, searching out that sparkling gleam that within sun's waning glory lies hidden to our sight. With hope, earth tears, the sky has washed clean. Then sudden the outcry, a joyous sight along that long-awaited sparkling gleam, and yes, a faint companion does remain. Perhaps that long-awaited kiss has passed, yet still hands clasp they before departing rest. With joy, earth's tears have cleansed, her darkened skies go crystal clear. The glass now is upswung, the pair drawn close to view, a sight not seen in time and space since years far distant gone. Wonder shakes our soul as earth's heart beats within our captured eye. Upon the darkened canvas of the sky, a sight scarce imagined fills up the eye. Wonder takes away our tears as awe in clarity dispels our fears. The pair long separated now, but in a spinning step apart, their finest attire to each displays. His wide girth with knotted belts holds fast his outflung diamonds circling. The other, his mellow hue enhanced with wide and glowing rings encircling. But we are not alone in seeking this far-flung joining. Those sparkling gems that upon the summer's warm breezes frolic on the glittering river's girth hold their passing to witness so rare a reunion's kiss. Fall's heroes also pause upon the crystal skies. As rabbit halts his rush into the night, each holds the long-awaited joining, prolonged and joyous in their sight. Only one, red-faced in anger, slips away, hiding from this wondrous sight behind Rabbit's brightening, shining light. Once more into the glass we turn, as still, hand in hand, they drop towards the missing sun. Now only as in a dream, a wavering image they appear. We cannot help but wonder now, will they meet and kiss once more upon some far and distant year? Okay, that was my impression of the day after conjunction. Thank you.
Thanks, Paul. That was delightful. And any questions for Paul?
I tended to put a lot of, I don't know, different images in the poem. So people might be able to pull out some of the sort of religious connotations, the physical aspects. The rabbit, of course, is the ears and the head of the rabbits on the quarter moon. Different mythologies and that. So I tried to blend what the sky was, because the summer sky was setting, the fall sky was rising, and it was just a phenomenal crystal clear night. Well worth being out and watching.
Just so you know, Paul, there are kudos coming through on the chat as well.
Thank you, everybody.
Okay, so thank you so much for that. And I do believe that Mr. Chapman, you are now up with what's up in the January skies.
Well, thank you, Judy. I almost gave it a miss because the weather has been so lousy this lately that I don't know what we're going to be able to see, but I'll cross my fingers and hope that we'll be able to catch a few of the things I'm going to talk about. I just wanted to make a couple of comments. You did mention that, no, this isn't working out. You did mention that people who join the RASC get the Explore the Universe
Yes,
guide.
yes.
But also not so well known is if you don't already have one and you're a member, you can ask for one. Is that correct, Robin?
I'm not sure, Dave.
Oh, I thought Phil Groff said that if anybody wanted one of these, they could just write in and get one. So
Okay.
You did.
He did?
and
Okay.
I know that you mentioned this, the lovely workbook that actually the RASC put out, I think to go along with the summer series, the Explore the Universe series we had this summer, which was very successful, and very pleased with how that turned out. I just wanted you to know that you can buy these from the shop. However, another little known fact is if you just want the insides, you can download that. There's a free download, and you can just print it out yourself or whatever. Just so you know, and you don't. I mean, it's nice to get one with the color cover, but you can get one for free from the Explore the Universe page.
So, and I have to acknowledge Dave and the work of others at the Halifax Center that put that workbook together. And it took, oh my gosh, sometimes getting things done takes time. I think it was 2 years, Dave, from the point where I asked if we could use that.
I wasn't counting.
I was, and it was painful.
No, it was nice for you to see that come together. And
yes, thank you.
And yeah, so actually, I was being on the observing committee of the RASC. We noticed that there was a big uptick in participation in the observing programs. If I'm not mistaken, it might be an all-time high in 2020, but a lot of that is definitely a significant part of that is people taking up the Explore the Universe program in response to the online offering that Jenna Hines and John Reed did. So there was a lot of interest. So congratulations back to the RASC for setting that up. So, okay, what's up? Let's see if I can do this. So I've been doing this for over a year now, which means I get to recycle stuff. It's not so much work. So I have done this using the RASC Observer's Handbook and Sky Safari to produce most of the content. This photo is courtesy of Dan Falk when he went to Easter Island years ago to see an eclipse of the sun. And he showed me a bunch of these pictures. And actually this picture, or a version of it, appeared on one of the observers' handbooks that I edited. It was almost the first one that didn't have like a nebula or something on the front cover or a galaxy. Maybe one that Roy Bishop had a space shuttle taking off or something. But I remember this was a bit different. And the reason I like this picture is because it's the Easter Island statues that we've all seen, but it struck me that it looked like they were looking up at the sky. And I really kind of, I like this picture, and a lot of other people did. So, all right. So the sun this month, well, somebody mentioned that the sun was picking up. It is picking up. It's a lot more active. We had a big sunspot group there last month at the end. I can tell you without a doubt that today there are no sunspots on the sun because I had a look. Plus, you can go online in the upper right-hand corner. There's a link there. If you go to our webpage, the RASC webpage, this presentation is there online, and all of the links are active. So you could go. I'm not going to go there now, but if you want afterwards, you could go there and see the sun in as many wavelengths as you want. But I did have a personal look through my solar telescope, and even though there's no sunspots, there's about a half a dozen prominences around. There's a couple of really nice ones, and there's a few little other details you can see if you have a solar telescope. And by that I mean one which transmits hydrogen alpha light. But if you just look with a solar filter on your regular telescope, you're going to see pretty much a featureless disk today. So I'll save you the trouble. So we're getting away from the solstice, but between the beginning and end of January, there's not a huge amount of change. There's a little bit more daylight in our day and a little less darkness. But next month, we'll really begin to see a big change in the day and night. So by the end of the month, we're going to get to almost 10 hours, and the sun will be higher up in the sky. And that's when, you know, me as a gardener, I'm not going to be gardening in February, but when the sunshine is longer than 10 hours, then you can actually think about growing things, you know, in the sunlight, because you need about 10 hours of sun to grow most things or to start plants or whatever. So the gardening part of me is looking forward to the end of this month. These little dials that I created in a program called Mathematica, I include these every month. But if you want to watch a little video that shows the whole year going by, there's a link to the YouTube, our YouTube channel, where you can watch that as a little animated video. It's kind of interesting to watch the ebb and flow of light and dark through the year. The moon this month, well, the last quarter is behind us now. Is that correct? What day is it today? I'm having trouble. Yes, it is behind us. It is the chief moon time for the Mi'kmaq. On January the 11th coming up, there'll be a nice pairing of the moon and Venus, a crescent moon and Venus. Before sunup in the southeast, they'll be about 5 degrees apart in binoculars, and maybe it might be a photo op for anyone who likes to get up that time of day. I might go out and try to get that. The new moon is on the 13th, and that will start a new Mi'kmaq moon time in the Puna Mujuyus. And I'll do that at the end. I'm going to try to do the video this time of that. In the next lunar cycle, there's going to be an interesting couple of days where the crescent moon is near Jupiter, Saturn, and Mercury in the southwest, but very, very low to the horizon. But it's something to look forward to if you can situate yourself appropriately. The first quarter is on the 20th, and on that day and the next day, I wouldn't say, you know, the moon is near Mars and Uranus, not super near, but if you're looking for Uranus, that's a good, you can use the moon as a guide for that. And then of course the full moon is on the 28th of this month. Now, if you go to this PDF online, follow the link and you'll be able to play that and hear the audio. I thought I checked it before and it worked, but it's the curse of Zoom. Anyway, Punamujuagoose. The tom cod is a species of codfish that lives in brackish water at the mouths of rivers. And for some reason, they decide to spawn in January and they swim upstream. And so for the Mi'kmaq and other native peoples living inland, they can fish them through the ice, the tom cod, because they swim upstream to spawn. And that's why it's called the tom cod spawning time. Anyhow, Curtis, the language teacher who did these videos with us, he told me as a child he remembered going fishing for tom cod. So again, I encourage you to at least do the lunar part of Explore the Universe, and there's a special map for this. That's in the Explore the Universe guidebook. I think that's the only place it's available. But it's a subset of the Explore the Moon program, and all of these items are from the handbook map and list of features. But this is the sub list, which is in Explore the Universe. So there's 12 craters and 12 mare that you need to observe half, like 6 of each of those. And I'm circling the center portion of the moon around the first quarter, when the moon is well positioned in the sky. There's quite a lot of real estate available to see on the moon. So like the 2 or 3 days around first quarter. So I'm saying that, that's a good time to go out with your telescope and snag a number of these features. I mean, you can go anytime, but if you've only got one cold night to go out in January, try around first quarter and you can knock off a few of those. So the challenge is try to find 3 at each. And as a reminder, the first quarter is on January the 20th. The planets, okay. Mercury, I'm not even sure, maybe even tonight, Mercury might be high enough in the sky just after sunset, maybe half an hour. And it's going to be, in the next few days, it's going to be in the vicinity of Jupiter and Saturn. Tomorrow night, if it's clear, it'll make a nice little grouping. Mind you, Jupiter and Saturn, and of course Mercury, are going to be very low in the southwest sky. So you need to have a really good horizon, and you shouldn't wait too long after sunset to get set up if you want to observe or photograph that. Mercury is heading for a greatest elongation east, which means it's in the western sky on January 24th. But you can look about a week on either side. You should be able to find Mercury in the twilight. It may help to use binoculars. It's fairly bright, but you never really see Mercury in a dark sky. It's always in the twilight, so you sometimes need help. Jupiter and Saturn aren't gone, but they're getting harder to see. I can't see them from home. I have to go somewhere. Venus, I've been seeing Venus in the morning, every morning, and it's getting very, very low in the southeast. It's headed for a superior conjunction in late March, but it is very slow moving in the sky, but it's not very easy to find. You have to catch it just right. It has been much more prominent in the morning sky throughout the summer and fall. But again, it's going to be near the moon on January the 11th, for those that like that kind of thing. Mars is still hanging around. It's going to hang around for quite a while. It's not as bright as it was, but it's still a significant red star. I was pointing that out to my 5-year-old grandson the other day, that Mars, I told him it was Mars. I also showed him Betelgeuse, which surprised him because he doesn't know it as a star. He knows it as something else, but I got him started anyway. And again, if you're looking for Uranus for your Explore the Universe, over the period of January 15th to the 28th, if you can find Mars, you can find Uranus. And it's closest on the night of January 21st. So there's a 5-degree binocular field. I've got Jupiter and Saturn crossed off. I mean, yes, you can see them in the sky, but I think any telescopic observation of them is going to be not very satisfactory. There's going to be a lot of turbulence, and the images aren't going to be great. Uranus is there in Aries, and sorry, I spelled Aquarius wrong. Neptune's in Aquarius. Definitely a telescope object. Okay. Now, speaking of Explore the Universe, this is our second month that we're going to do the winter constellations. These are fairly easy to catch because they all have bright stars in them. So again, if you're doing Explore the Universe, go out on a clear night after dark, which is not too late, and you should be able to pick off all of these, you know, Auriga, Gemini, Taurus, Orion, Canis Major, and Canis Minor. And of course, they have bright stars that go along with them. So the winter stars in Explore the Universe in rank of order: brightness, Sirius, Capella, Rigel, Procyon, or is it Procyon? Betelgeuse, Aldebaran, Pollux, Castor, and for some reason, Gomesia, which is the second star in Canis Minor. I don't know why they picked that out and not other stars, but there you go. There you have it. So interestingly enough, many of these are navigation stars that are used for celestial navigation. And all of them are, if you have a SynScan go-to telescope, all of them are good for aligning your telescope to the sky. Again, fairly easy to do on a clear night, lots of bright stars there. In terms of the deep sky objects that are available, most of these are star clusters, but there is the Orion Nebula. The other ones are star clusters, and Campbell's Cascade is an asterism named after Lucien Campbell, who is a noteworthy member of the RASC, now since deceased. However, as part of or close to Campbell's Cascade, we have a nice little cluster, NGC 1502. You can pull out Campbell's Cascade easily in binoculars. The star cluster may just look like a fuzzy patch, but once you've found it, Judy has a way of finding it pretty easy. I forget it, but she knows. Maybe she'd share that with us.
I use Cassiopeia and use the two stars that are the furthest apart. And
Okay.
they go that same distance away, and it's in that general vicinity, going towards Auriga from Cassiopeia.
Thank you for that, because it's
That's
pretty
Melody Hamilton who showed that to me.
Yeah, okay. It's in a pretty unremarkable part of the sky. The constellation it is in, it's called Camelopardalis. Pretty obscure, but anyhow.
It looks like a
the
hot
challenge is,
when you look at it.
what, the Cascade?
Cascade, when you look at it, goes down in a line, and then NGC 1502 forms the tip of the stick.
Okay, well, that works. Anyway, the challenge is to find that in your binoculars. It's quite high up in the sky, no excuses. You should be able to find it. It will take you like 5 minutes, right? So put on your parka and your thick socks and your toque. And I'm bringing this up again, Algol. I mean, you can see Algol, you know, most of the year you can see Algol, but in the wintertime and the fall too, you've got some really nice long dark evenings to observe Algol. And I picked out a couple of dates where, and you can do this naked eye, you could use binoculars too, but it's an eclipsing variable star. And on these dates in January, weather permitting, you can either watch the Algol fade from full brightness down to its minimum over a period of hours, or you can watch it on another date. You can watch it brighten from its minimum to its brightest. So for that, you know, you just time it and go out every, I don't know, 20 minutes or 40 minutes or half an hour and just have a look at it and see if you can notice the brightness change. I mean, you don't have to you could try to estimate the magnitude and all that, but I think it would just be fun just to look and see how it appears to you from one time to the next. So it's an eclipsing binary, which means that the reason it varies in brightness is that there's a star which circles it and blots off the light with great regularity. And it just so happens that the orbit of the secondary star is lined up such that this happens. I believe it was the first variable star I ever noticed.
Dave,
Yes?
I believe the Explore the Universe program suggests that you compare Algol to 3 or 4 other stars that are in, as part of Perseus and Andromeda, so you can get an idea
Yes.
of how bright it is as far as magnitude goes.
Yeah, if you want to go to that level, in the Observer's Handbook, there is a finder chart with magnitudes marked. And I believe, I mean, you can go further and go to the AAVSO site and get, you know, you can get all kinds of information for that. I'd be happy if people just went out and had a look. I just kind of qualitatively saw it brighten or fade. Estimating magnitudes and that, you know, kind of a next step. I did want to say one thing about Explore the Universe. I didn't include the double stars. The double stars in Explore the Universe for the winter is not a very significant list, but I did want to say that the RASC now has an official double star program of 110 objects, which was launched a few months ago. And we hope to, at some point in one of these meetings, talk about that. But it's there, and all the resources are there. I've done a few of them, and it's a lot of fun. And you know, you can you have a list of targets. You go and you have to identify where the star is and go have a look. So the way I'm doing it is, I don't know all the information about the double star when I go. All I know is that there's a double star, what its effective magnitude is, and where it is. I go and look at it and see what I can see in my telescope, and I draw the pattern. And usually it's pretty obvious what the double star is. Sometimes not so much. But then I go back and look at the supplementary list and see what I should have been seeing. And it's fun to do that way because you know, you sort of partly discover what's there rather than knowing it all before you look. And sometimes you have to go back and look again. There's nothing wrong with that. Yeah. But it's a fun thing to do, and you can do it with a fairly modest telescope. And when I say you draw it, I mean it's just like putting dots on a paper in a circle. Like, it's the easiest thing. It's not even drawing. It's just putting dots on a paper. So anyway, something you might want to look into. It's online if you want to check it out. And with that, I will open the floor to questions. Okay, I guess everybody's.
Was that last image what we expect to see with Venus and the moon, or Uranus and the moon? That last image?
The last image is just a picture.
The moon should be in that phase though, shouldn't it? Or, I mean, granted, the curve will be on the other side.
No, it's not what you're going to see with Venus. That picture is just a picture. I tell you why that picture is there. I took that picture in Cuba a couple of years ago. I think it's maybe Mercury and the moon. And I've got the Jones for going to Cuba right now, and I can't go. So the best I can do is have this picture in my slide presentation. I'm not going to be able to go down there and see my friends and walk on the beach and all that, and it's hurting. But given everything else that's happening in the world, I shouldn't complain. So it's going to be a long, cold winter here. Okay.
Okay. Well, thanks, Dave. Up next is me, I guess, in the news from the board. So again, Happy New Year, everyone, and welcome to 2021. If you need to or look us up, you can search for halifax.rasc.ca. That's our main website. If you need to reach me to ask any questions, I can be reached at president@halifax.rasc.ca. I want to remind members that we do have the RASC calendars here for sale. All you have to do is send an e-transfer to our treasurer with your name and your mailing address in the messages portion of your e-transfer. That way, because sometimes email addresses don't give us a name. They have this neat and wonderful other name other than the person's name. And that way we can get it to you. Keep in mind that there are 3 of our members who are included in that calendar this year. Keith Egger in April, Jason Dane in August, and one of our youth members, Fiona Morris, in October. So it's a wonderful product, and it's still early in the year. So please send an email to our treasurer, Greg Dill, and he'd be happy to send it off to you. As most of you are aware, our St. Croix Observatory is in the process of undergoing an upgrade to its electrical capacity. And our goal was $7,500. And thanks to the very generous members that we have, we've surpassed that goal. And currently we have $8,210 raised from those donations. Thank you, everyone. Keeping in mind that everything that comes in, has come in and continues to come in, will be kept for SCO upgrades and for ongoing maintenance of the facility. So although we do have enough to fund the electrical upgrade that we are currently doing, we could certainly welcome more funding for future work at SCO. What has been done so far is that the pole has been put onto the site from the main electrical line that goes past the facility. And we have hired an electrician who I believe will begin next weekend to do the external electrical work. There might be a possibility that there won't be electrical power at the facility. That would include all the lights in any of the 3 buildings and all the outlets. However, that is only a possibility. The hope is that they will be able to retain that electrical capacity. We'll keep members apprised as things unfold. If you don't hear from us, all is well, electrically speaking. The other thing that we had in relation to fundraising for SCO, and this will be an ongoing venture, is 3 of our Astro imagers, Jerry Black, Jason Dane, and Blair McDonald, agreed to provide some of their images that they've done over the past year or so and have donated them for us to sell. The $357.52 that you see there are the profits realized from those sales. So thank you very much, those 3 souls, for donating their time and effort in relation to the production of those images. And thanks to Blair for overseeing the distribution of those that are sold. As most of you are aware, in December at our AGM, there was a new board of directors that were elected. You see them there. I am president. Pat Kelly was newly elected to the vice president position. Peter Hurley and Greg Dill have retained their position, and Mary Lou continues to be our honorary president.
Judy, can I interrupt for a sec? Had you meant to share your screen?
Yeah, is it not shared?
No, all we're seeing is you.
Oh, fudge. All right, then. Let's do this, shall we? Sorry. How's that?
Yeah, that's fine.
Okay, my apologies, people. Yes, so as I said a moment ago, I am the president. Pat has been newly elected to the vice president position. Peter and Greg have retained their position as secretary and treasurer respectively, and Mary Lou returns as our honorary president. Tim Doucette and Kathy Walker are new members to the board, so welcome. And also there were newly appointed positions that are also in effect as of the beginning of the year. Ian Anderson is returning as our auditor. Dave Chapman now has a co-chair, Tony Schellink, for the Dark Sky Preserve Committee. I continue to chair the Governance Review Committee. Wayne retains the librarian position, and I've stepped in to replace Pat as the national rep on National Council. The nominating committee chair is Peter Hurley. We'll address Nova East in a minute. We have 2 new co-editors, John McPhee and Lisa Ann Fanning, for Nova Notes this year. So we're looking for some exciting things happening there. And a great thank you to Charles White for his work over the past 3 years in that capacity. Observing chair and outreach chairs continue to be Dave and Paul, and our SCO manager, John Ledard, who is overseeing this upgrade extremely well, and it's keeping him busy. We hope to continue building our relationships over the coming year, building that bridge between our center and Ketchum-Kujik National Park and National Historic Site with the Dark Sky Preserve there, as well as with the Discovery Center in providing various programs with them. And just a reminder for members, if and when you do conduct outreach, let us know if you're having an event, whether or not you need members to assist you. But do remember that you do have to meet the COVID-19 provincial restriction requirements when you are organizing these events. The way to go about it, if you need assistance, is to go into our discussion list, and the subject title should read Outreach Request. And once this event has been completed, please report it with the subject in your discussion list subject, Outreach Report. And that way we can keep track of events and the numbers for our center that you have reached.
Judy,
Yes,
may I make a comment on outreach there as well?
sure, please.
So if any members are doing a public outreach and you want to have the society liability insurance applied to that, you do want to register that on the RASC website, and you'll get a certificate for your particular event, and that will ensure that you've got that liability coverage from the society office.
Great, thank you, Robin.
Yeah.
Welcome.
For local here, those that are looking at the school, once you've got your time and that set, I do have the handouts and everything here, so contact me and we can make arrangements to get all that outreach material to you before your presentations.
Great, thank you, Paul and Robin. RASC observing certificates. As Dave mentioned earlier, there has been a significant uptake in the number of certificates or programs that have been completed, and the Explore the Universe is certainly one of them. Halifax Center has had 6 members complete the Explore the Universe program this year, and the latest is Elsie Ferguson, who completed it on December 11th. So congratulations, Elsie. Well done. One of the other things I'd like to point out are our Halifax Center stars. When some of our members get published either in our publications or get noticed elsewhere, I'd like to make note of it. Sky News, the latest edition in January, February, Lisa Ann Fanning, one of our newest members, in fact, I think I'm correct in saying this, Lisa Ann, is that you became a member of Halifax Center and of RASC as of this past January. And to have your name published or to have your article published in Sky News is incredible. And as you noticed earlier, Lisa Ann is also our co-editor for Nova Notes. So new member, but really engaged. So thank you. Also, Mike Gatto, he's been an incredible, I don't want to call him a sketcher because this goes beyond sketching, the work that Mike does, but in the Journal of the RASC is his latest production, and that's the Lunar Escape. And I'll let members read the latest edition as to the details on that particular. So congratulations to both Lisa Ann and Michael. So I mentioned at the beginning of the meeting that you can become a member. You can join online. For those of you that are comfortable doing that, if you aren't a member already, you can certainly go to our website in About Us, and you'll find this column called Becoming a Member, and you can click on Join, and you can do that online. If you are uncomfortable joining online and you prefer the old way of snail mail, click on Form, and you can certainly join us that way to get the form to complete and mail your payment in to RASC. Now that's for national, but for us here locally, you can also consider our own perks, which is our email discussion list and also information about our St. Croix Observatory and how you can, what the facilities are at the observatory. One of the things I'd like to do at the beginning of this year is to thank everyone for all their work over the past year. That includes all the members. All of you have been absolutely incredible in the past year. As president, it's been my honor to represent you at meetings that I have had to attend. And we know that that little critter has been a detriment to the way we have done things. Our year began well in January, February, March. We were able to conduct business as per usual. But come the end of March, that little creature changed things and how we did business and how we conducted business. We were hoping he'll just disappear. But what has happened over the past year, it's been amazing. With respect to the St. Croix Observatory, once COVID hit, we had to develop guidelines for using that facility. And we've also had, as you know, as I mentioned earlier, the fundraising to upgrade the facility so that when we can come together again, we have the capacity electrically for people to use it. With our outreach, as I mentioned, our numbers are certainly down, but then with COVID, that's not surprising. But there have been outreach events despite it. And as I mentioned, also at the Discovery Center, we're going to continue working with them to provide some of these outreach events under the COVID restrictions. With InReach, we've had several events there. Our Nova East, which was a camping event, became a speaker series. We had Zoom sessions for International Observe the Moon Night, and we've had virtual lunar observing sessions. With astroimaging processing, we've had introduction to processing, how to use the two programs, PixInsight and Images Plus, as well as a session on lucky imaging. We've had members meetings through Zoom, as we are doing now. We had our AGM on YouTube, and we had a special meeting, a members meeting on requisition regarding SCO, and all of these have been recorded and are currently on our RASC Halifax YouTube site. For those of you that have missed any of them, can review them. Our board of directors also utilize Zoom following the lockdown here, as have the committees that they oversee. National committee members, can't thank you enough for representing our center so well. And although I haven't named all the other people that are involved with all these others, I would like to make note of these national representatives. Dr. Roy Bishop on our history committee. Pat Kelly has been the national council rep for numerous years in the past. Keegan Oikel, one of our youth members, is on the Next Gen committee. Melody Hamilton on observing. Blair McDonald on astroimaging. Paul Heath on the inclusivity and diversity committee, and Dave Lane on the information technology. So we have quite a few members that are involved at the national level. Also want to note the education that we were able to provide using our YouTube and other methods. Various members have provided videos to us using binoculars, buying a telescope, laser collimation, and again, all of these videos are on our RASC Halifax YouTube site. And how do we keep in touch with each other? Through our website, through Nova Notes, our newsletters. And by the way, our November-December issue of Nova Notes will be posted within the next 24 hours. Our announce list, which apprises all of our members of what's up and coming, and certainly the Rascals discussion list here locally, keeps a group of people asking questions of each other with respect to equipment, observing, processing, you name the topic is discussed. So yes, it's been an incredible year with many people being involved. And because of that, our center is quite active and a vital center. So I thank you for that. And what's really cool for me to note is that in all of this going on, that it isn't just the new members that are learning over the past year through these, it's also the more experienced observers as well. And so to that, I commend all of our members across the center for doing that. So ask me anything, any questions? I guess we don't have any questions. So given that, the formal part of our meeting is now over, and I thank everyone from across the country for attending. Robin, as the national president, I thank you for being here with us today. And for those members who are from across the country, welcome as well, and hope to see you again at one of these meetings.
Thank you, Judy. Thanks, everyone. It's nice to see you all. I was really hoping to get down to Halifax for a meeting, but COVID's kind of put the kibosh on that. I usually come to Nova Scotia once every couple of months. My mom is in Sydney. And I was hoping that I was going to plan a trip that would align with one of your meetings, but I don't think that's going to, I'm outside the bubble. I'm not allowed in the province.
In the province you're in, you're definitely most outside the bubble. Yes.
That's right. And I usually have to spend at least a week in Cape Breton to get my accent back.
Well, we'll certainly welcome you whenever you're out east again, Robin, and hopefully that can happen in the coming year.
Yeah, I'm sure it will. I'm sure it will. Thanks, Judy.
Okay, so I'm
Nice to
going,
see everyone.
thank you.
You too.